So in the previous class, we started discussing a little bit to what is a sinusoidal. So remember that the sinusoidal is basically a trigonometric function that can be expressed as either a cosine wave or a sine wave. Okay? And these trigonometric functions have an amplitude, that is this term right here. We have a frequency and we have a phase angle. Okay, and this angle is often measured in degrees. Okay, and basically the phase angle is telling us about the displacement of the sinusoidal across the horizontal axis. Okay, so now one of the things that I want to introduce is the idea of how you can compare different sinusoidals. Okay, so in order to compare different sinusoidals, we can analyze them in terms of lagging and leading. What what is the meaning of all of this? When the meaning of leading basically means that, for instance, if we analyze these two sinusoidals, you can observe that the red sinusoidal that is described by this equation is crossing the horizontal axis first compared to the other one. Okay? That is the green sinusoidal that is expressed or represented through this expression. So when we talk about leading, basically means that one of the sinusoidals is crossing the horizontal axis first compared to the other one. And when we talk about lagging, basically means that the green sinusoidal is crossing the horizontal axis after the red one. Okay? It's lagging because it's crossing the horizontal axis after. Okay? And basically, we can also interpret this as which one of the two sinusoidals we are measuring first. And in this case, it appears that the red sinusoidal is being measured first compared to the other one. Okay, and another important parameter that we want to consider is that sometimes we also want to determine what is the distance between the two sinusoidals when they cross the horizontal axis. Okay, so we want to measure this distance, and this distance is essentially the phase difference between the two sinusoidals. So here in these sinusoidals, we don't have a phase angle, so we can say that the phase of this sinusoidal is equal to 0 degrees, but here we have a phase angle theta. And the difference in the phase angle, that is theta minus 0, is the distance between the two sinusoidals, or the phase difference between the two sinusoidals. Okay, but aside from that, it is important to consider that we have to meet certain conditions in order to compare two sinusoidals. The first one is that the amplitude of the two sinusoidals must be positive. Okay, here you can observe that, well, we have a positive amplitude sinusoidal. Also, the frequency of the sinusoidals must be the same. And another important factor is that the sinusoidals needs to be expressed in terms of the same trigonometric function. Here we are comparing a sine wave with a sine wave, okay? But for instance, if this sinusoidal was a cosine wave, I cannot compare it with a sine wave. So I need to convert or express the two sinusoidals as sine waves or cosine waves, because we cannot compare a cosine wave with a sine wave, at least in terms of leading and lagging, okay? And also to compute the phase difference between them, okay? So, well, let's continue. So this is basically um, the conditions that we must consider to compare the sinusoidals. But before that, it is important that I mention that, well, when we have different phases for the sinusoidals that we want to compare, we say that they are out of phase, okay? But when they have the same phase angle, we say that they are in phase, okay? So that is very important to consider. Another point is that, well, we need to consider this phase, well, sorry, these conditions in order to compare them. Here, We are talking about the frequency, the amplitude must be positive, and also both should be expressed as cosine or sine waves. And another condition is that we need to express the phase angle of the sinusoids between 0 to 180 degrees. So this range will be from minus 180 degrees to 180 degrees. No, that is the range of phase angles in which we can express them. Okay, so that is the meaning of this condition. Okay, we need to express the phase angle between this range. Okay, in order to compare the sinusoidals. Well, so since one of the conditions is that we must express the two sinusoidals as cosines or sine waves, well, we can use certain identities. For instance, this identity is useful when we want to convert a negative sine wave or cosine wave into a positive sine or cosine wave. Here we have a negative cosine wave, and if I want to convert it to a positive cosine wave, I can add or subtract 180 degrees. But here we also have a negative sine wave. And if I want to convert it to a positive sine wave, I can add or subtract 180 degrees. Okay, so that is very, very important. Okay, so if you want to convert a negative sine wave or cosine wave, basically what you can do is to add or subtract minus 180 degrees to the argument. Okay, so that is a very important condition. Another identity that is very useful is when we want to convert the sine wave to a cosine wave. So for instance, if you have a negative sine wave, no? Here, well, you can see that we are denoting two symbols, the negative and the positive sign. So if you have a negative sine wave, if you and you want to convert it to a positive cosine, you can add 90 degrees to the argument. On the other hand, if you have a positive sine wave and you want to convert it to a positive cosine wave, you can subtract minus 90 degrees to the argument. Okay? So this is what this identity is telling us, no? We can convert a sine wave, either is negative or positive, to positive cosine wave uh, by adding or subtracting 90 degrees. If you have a negative sine wave, you can add 90 degrees. But if you have a positive sine wave, you need to subtract 90 degrees. Okay? Another identity that can be useful is the following one. Here you can see that we have a positive cosine wave. And if you want to convert it to a positive sine wave, you need to add 90 degrees. But also you can have a negative cosine, and if you want to convert it to a positive sine wave, you need to subtract 90 degrees. Okay? So this is very useful when you want to convert a cosine to a positive sine wave, but you need to take care of this condition. No? Based on the amplitude or the sign of your amplitude, you need to add or subtract 90 degrees, and you need to follow the relationship of these signs, okay, that are placed right here, similar to the previous identity. Okay, so, well, this is for the identities. So I think that it is useful that we make some exercises. So in order to do that, let me a moment, let me try to share my screen. Just wait a moment. Just a second. Just let me a moment. I need to share the screen of my tablet. So the screen of my tablet is as follows. Well, I think I need to change um, the Wi-Fi network. So let me do that just a second. I need to change my network. Okay. And now I can share the screen from my tablet. Just 1 second. And here I need to share the duplicate screen. Okay, now I have encountered that. So let's wait a little bit in order to share the screen now. So I would like to recover the exercise that we have. So let me go to my notes here. And well, let's make a new page right here and let's write, well, let's place everything in its place to start. So in the exercise, we have two sinusoidals. Here we have B1 that is equal to plus Bn1 times the cosine of 5 times t plus 10 degrees. And we have another sinusoidal that is B2 that is equal to Bn2 times the sine of 5 times t minus 30 degrees. Okay, these are the two sinusoidals that I want to compare. Remember that we need to first check for the conditions. So one of the conditions, according to what we have seen, is that the two sinusoidals must be positive or have a positive amplitude. So in this case, we don't know the exact, we do not know the exact value of the amplitude, but according to the problem, we have a positive amplitude right here. Also, if you compare the frequencies of the two sinusoidals, you can see that they are the same. The frequency is equal to 5 radians over seconds. But the problem here is that we have here a cosine wave, and in the other function, we have a sine wave. So the first step will be to convert the two sinusoidals into the same trigonometric function. So to do that, I will convert the sine wave that is right here into a cosine wave. So remember that we have this identity that is that the sine of omega times t, if we have a positive sine wave, is equal to a positive cosine wave of omega times t if I subtract 90 degrees, okay, to the argument. So I can subtract 90 degrees to the argument. That will be equal to B2 is equal to Bn2 times the sine of 5t minus 30 degrees minus 90 degrees. Okay. Sorry, I committed an error there. Sorry. I I forgot to place a step right here. Sorry for the trouble. So here I need to write again the function in order to be clear about the procedure. So we have here Vm2 times the sine of 5t minus 30 degrees. And I need to subtract minus 90 degrees to the argument. So this will be equal to Vm2, okay, times the cosine of 5t minus 30 degrees minus 90 degrees. Okay, and this will be equal to Vm2 times the cosine of 5t minus 120 degrees. Okay, this is the phase angle that I need. So now I have converted both sinusoidals to cosine waves. Now I can compare them. So I will write right here Bn1 again. Bn1 is equal to Bn1 times the cosine of 5t plus 10 degrees. Okay, so if I want to know which one is leading and which one is lagging, what I can do is to first plot the phase angle across an horizontal axis. So this axis will be the position of the phase angle. Okay, I will label this axis theta, and I will place the zero phase angle degree in this position. And you can see that for B1, we have a phase angle of 10 degrees. Okay, and for B2, we have a phase angle, now that I have converted the sine wave to a cosine wave, of minus 120 degrees. So we have here B2 and has a phase angle of minus 120 degrees. This is like an approximation, it's not exact. It's only to locate where in this horizontal axis this phase angle will appear. And if you look into these two faces or phase angles from this perspective, now imagine that you are right here, you will notice that the first one is V1, and the one that is behind is V2. Okay, so we can say based on this reference is that V1 is leading V2. Okay, if you look at the two faces from this perspective. Okay, and as a convention, will be the way in which we will be analyzing the two sinusoidals. Okay, from this reference. Okay, or look it always at the waveforms from this perspective. Okay, and another thing that we need to compute is the phase difference between them. That is basically the distance between them. So here we have a 10 degrees for V1 minus 120 degrees. So this is the phase difference between them. And this will be equal to 130 degrees. So we can say that V1 is leading V2 by 130 degrees. Okay, and this is the way in which you can compare two sinusoidals. Remember that you need to verify the positive amplitude, you need to have the same frequency, and also you need to convert the two sinusoidals into the same trigonometric function. Here in this example, we convert the sine wave to a cosine wave in order to compare it with the V1 that is also a cosine wave. And now that you have that, what you can do to know which one is leading and which one is lagging is to plot across an horizontal axis the phase angles, okay? And based on that information, and if you look at the phase angle from this perspective, you will notice that the first one that you will encounter will be V1, and the following one will be V2. So we can say that V1 is leading V2 by the difference of the phase angles, that is 130 degrees. So this is like a brief introduction related to comparing two sinusoidals. I hope you like this video, and if you have a comment on our question, you can tell me. So thanks for watching.